the C++ is such a tight-knit community, and it's awesome to have events like this where everybody can kind of immerse themselves in, mingle, and then get to know each other on a social basis and on a professional basis, while having some really good content that you can learn from as well.
All right, hello everyone and welcome to our CppCon talk. We're going to talk to you about two really exciting new tools coming in LLVM 20 specifically for the real-time programmer. One is called Realtime Sanitizer and the other is called Performance Constraints Attributes. You will hear all about it in just a second. Before all that fun stuff, while people filter in from snacks and everything, we're going to get through the boring boilerplate. Who are we up here on the podium here today? My name is Chris Apple. I'm a 10-year veteran of the audio industry. Specifically, I've worked at companies like Dolby and Roblox and Spatial Inc., a startup that works on audio things. Currently, I'm a full-time cat trainer, so if you have any tips on how to, I'm trying to get my cat to jump into my arms with treats. It's very difficult. If you have tips, I'll trade you for Realtime Sanitizer tips later. This is my friend and colleague, David. He has 15 years experience in academia and startups, including places like TikTok and Imperial College in London, and currently is an audio software consultant. So if you have some audio software consulting needs, please hit him up after the talk. More crucially, though, we are two of the three authors of Realtime Sanitizer, this new tool that we will introduce in just a little bit. We also want to extend a very special thanks right up top to Ali Barker, the other author of Realtime Sanitizer, who couldn't be here today, and Doug Wyatt, who wrote the Performance Constraints Attributes. All right, what are we going to cover today? The first half of the talk, I am going to go over real-time programming basics, if you haven't heard of the concept before. We're going to go through some existing strategies to look at real-time safety violations. Then we're going to go over our two new tools, the stars of the show, Realtime Sanitizer and the Performance Constraints Attributes. And about the last, if we didn't choose, we went forward a little bit. The last half of the talk will be kind of comparing and contrasting these two tools and giving you some practical tips on how to use them in your code bases today. So first off, what is real-time programming? Some of you may have heard of the concept, others may have just been hearing this for the first time today. I actually think Wikipedia does a pretty good job at defining real-time programming. So real-time programs must guarantee response within specified time constraints referred to as deadlines. So there's a lot of dramatic language in this definition right away, specifically deadlines. Do your work by this line or drop dead. Very dramatic. Real-time programs, in particular, need to provide the right answer and provide them in the right amount of time. Normal programming, all code strives to be correct. You want to write your calculator app to provide 2 + 2 = 4, but real-time programming is defined by giving an answer in the correct amount of time. If you fill an audio buffer, but you're 10 milliseconds too late, that audio buffer is as good as garbage. All right, we've established that returning too slow is bad, returning after the deadline is bad, but what are the consequences? These often vary by industry. In audio, where David and I work, the consequence is what's known as a dropout. If you've ever been listening to Spotify or YouTube and heard an unexpected crackle or pop or static or unexpected silence, you've heard a dropout in action. It's more than an inconvenience, though. I used to work on a product called Dolby DJ, which was installed in nightclubs. A dropout at 130 decibels is, you might blow out your speaker, you might blow out a patron's eardrums. It's going to be messy, it's going to be expensive. On the input side of things, if you are recording a once-in-a-lifetime performance like the 100th anniversary of the London Symphony Orchestra and drop out on input, you've dropped some valuable history on the floor that might never be heard again. In aerospace, missed deadlines are dangerous or expensive in a different way. If your navigation algorithm diverges from reality over time, at best you end up in an orbit that you didn't calculate, and at worst you find the Atlantic Ocean with your rocket. Several systems in autonomous vehicles have to deal with real-time constraints. If the perception system misses a deadline, you might miss something really important like a child appearing in a road or a car swerving into your lane. A car driving an outdated plan for too long will miss important signals like red lights, or they might hit another vehicle. All right, we've established real-time safety is important. The consequences are bad. So what does real-time code look like in C++? In audio, it might look something like this. David or I might call this a process block or a process audio block, something like this. The idea is you fill an audio buffer every n milliseconds or suffer the consequences. Generally, these functions are called on a real-time thread, which is a highly promoted thread that says the operating system gives you a specific time slice of processing time to do your very, very important work. In aerospace and other industries, this is known as a dispatch loop, but the idea is essentially the same. Process this data in the given amount of time or else. In these blocks, code is confined to very specific worst-case execution times. Worst-case execution times in a dispatch loop or process block must be deterministic, it must be known in advance, must be independent of input data, and shorter than the given deadline. Thank you, Timur, for this definition a few years ago at CppCon. So we'll come back to this idea of determinism time and time again. But before we get into that, you might be asking yourself, I don't really care about any of this. What's a few nanoseconds between friends? If it's non-deterministic, but we don't really care about that. Well, I'm gonna give you a little bit of a spoiler. Malloc is real-time unsafe. It's one of the key calls that is real-time unsafe. And how long does it take? Well, depending on your operating system and processor and everything going on, it might take 90% of the time on the order of 10 nanoseconds, pretty fast. But as real-time programmers, we're not worried about the 90% case. We're worried about this 1% of the time that it goes as slow as a millisecond. You can see this huge jitter in values can really kill your deadline. Now, when you're dealing with real-time callbacks on the order of milliseconds like audio, or maybe you have a really small buffer in the order of microseconds, or some real-time operating system medical device, you can see how an additional millisecond floating around here would really, really be problematic. So some of these non-deterministic calls on top of malloc, which we just talked about, things like system calls, asking your operating system to do any work on a shared resource. Allocations, mutex locks and unlocks, thrown exceptions, indefinite waits, and the list goes on. We, as real-time programmers, have these lists in our head when we're programming, and we say, oh, make unique, that's not okay. Mutex lock, that's okay. And we keep all this complexity in our head. So what binds these all together is not only that they're non-deterministic, but they block the forward progress of our audio thread. We need to make sure that we keep making, or our real-time thread, sorry, I'm an audio guy, I'm gonna keep saying audio stuff. This is all real-time appropriate, I promise. It blocks the progress of our real-time thread. So we need to make sure that we remain non-blocking. We can continue forward progress in these threads. And remember this word, it's gonna become really important in this talk in a few slides. All right, so what do violations look like in code? If you were doing a code review, could you point out the real-time violation? Sometimes it's extremely obvious. Mutex lock, you have a dispatch loop in a real-time thread, and it calls mutex lock. If I was a senior engineer on this program, I'd say, yeah, maybe go rework that. Maybe you should use something else here. I'm sure we all can agree that make unique somewhere under the hood is allocating memory. Allocating memory is real-time unsafe. Please go rework your code. However, these examples are pretty much as easy as it gets. Sometimes it's a lot more hidden. It's hidden from you, the code reviewer. It's hidden behind layers of third-party libraries or the STL. It's really hard to reason about on the surface level. How about this? What is numbers here? What data structure is it? Is it a vector? Is it a map? If it is a map, are we adding to an existing key, which might be safe, or are we allocating a new key? There's a lot of complexity here that we just don't know. How about this example? Posting a report, we're posting some lambda to this function. Who remembers if this is a std function or captures it by template? When does std function allocate? What sizes are appropriate as input variables or not? I don't know, don't ask me, I just wrote the slide. And further, the main problem here is, what if this changes over time? What if input array and output array, instead of giving 2 floats, next time gives 200 floats? This can change over time and ruin your real-time safety guarantees. And of course, the third-party example, we'll be coming back to this example time and time again. What is this third-party library doing under the hood that could be real-time safe or unsafe? How do we know that they're playing by the same rules that we are? This is the question that we come to time and time again, that we're asking ourselves every time we write code in a real-time context, over and over again. How can we be confident that our code is real-time safe? Which brings us to our next point. How do we prevent our rocket blowing up today? Well, there's a lot of existing strategies. Things like shared experience, telling a newbie what to do and what not to do. Code review, we just did some code review in the previous slides. Using profilers and debuggers, things like strace, dtrace, instruments, these are all really valuable tools. Static assertions, like the ones that can check if your atomics are lock-free. And documentation, big capital letters right on your function. Do not use this in a real-time context. I swear to God, do not do it. Maybe a little error-prone. All right, all these have their caveats, of course. Getting experience takes a long time. I've been doing this for 10 years, and I hardly feel like I know anything about it. Code review is really prone to human error. We saw that a couple slides ago. Profiling and debugging is very manual and time intensive. Are you doing this once a week? Are you doing this once a release? How often are you hooking up the debugger and profilers? Static assertions are limited in what they can catch, and documentation goes out of date. As soon as you hit your caps lock to type that big message, somebody else has already committed code, breaking that guarantee. And of course, what about pre-built dependencies? This is a real big problem. If you get a library from somebody else, how do you verify what's going on? But let's live in a utopia for a second. Let's live in paradise. What if we had a tool that could just tell us if things are real-time safe or not safe? A nice tool, if we were going to design this from scratch right now, it would assess real-time safety. That'd be the main component of this tool. It would detect a wide range of violations, mallocs, locks, things like that, even in third-party and pre-compiled dependencies, and point to any problematic code. It's not enough to print a message saying there are real-time issues in your code. Ideally, you'd like to be pointed to directly what the problem was. And of course, be able to fail a CI pipeline. Ideally, you'd be able to run this continuously and be notified as soon as there was an issue instead of later in your production code. Well, luckily for us, the future is bright. There are two new tools coming in LLVM 20 that help the real-time programmer. The Realtime Sanitizer is the runtime approach, and the performance constraints attributes are the compile time approach. These two tools were designed to work together and complement each other, and that's what we're here to talk about today.
All right, thanks very much, Chris. So over the next 10 minutes or so, I'm going to introduce the first of these. Realtime Sanitizer is the tool that Chris and I have been working on integrating upstream into the LLVM project over the last few months. Thank you. I'm going to cover two aspects of it. First, just a really quick intro to what it looks like and how to use it. But a bit more importantly, I'm going to dive into a bit more detail, try to look under the hood a bit and try to build an intuition for how it works so you can make your own decisions about what problems it's going to help you with and what problems it might not help you with. So, as a quick show of hands, I think we might know probably what the answer is, but who in the room has used a sanitizer before? Okay, great, the vast majority. That's fantastic. Keep your hand raised if it has helped you fix a bug. Yeah, of course. Okay, so clearly indispensable tools, right? Very, very valuable. So for the benefit of those of you in the room who might not have used one before or know what it is, I'm just going to do a very, very quick overview on this slide. We have some problematic code on the slide, right? We're allocating a vector and then trying to read outside the bounds. Now, what would happen if we just compiled this without any other instrumentation and tried to run it? We'd get a seg fault, crash, something along those lines. We'd have tried to read some memory outside of what the operating system had allocated to us. But if instead we knew about address sanitizer and we activated it with this single simple compiler flag, then that instrumentation can pick it up, and at runtime we get this really nice error coming out. Look. It's caught our heap buffer overflow, and critically it's pointed us exactly to where it happened. Example.cpp, line 6, column 12. So we can straight away go fix our bug. That's great. So what about Realtime Sanitizer? Right? We've got some problematic code on this side as well, but only if we know that process is a real-time function. Process is meant to be non-blocking. And what's happening here? Why is this problematic? Anyone want to tell me? Yeah, we're getting an allocation. Yeah, right there, we're constructing our vector. Now, using Realtime Sanitizer is almost as simple as using Address Sanitizer. We just need to do one more thing. And that's we need to tell Clang that this is a non-blocking function. So we attribute it Clang non-blocking. Then, just like Address Sanitizer, we compile and link with this simple compiler flag. And at runtime, Realtime Sanitizer catches this, tells us, hey, hang on a minute, there's an unsafe library call, and it points us directly to where the problem was. Example.cpp, line 6, column 14. So we can go and sort out our problem straight away. We don't need to do any more hunting. So, just to hammer this point home, this is how you use it. 2 steps only. Attribute your real-time functions with Clang non-blocking. Compile and link with fsanitize real-time. All right, now onto the more interesting bit. How does it actually work under the hood? So the algorithm behind Realtime Sanitizer is actually really very simple. It's just really about the interaction between 2 cooperating components. One component is a lightweight runtime library that gets linked into your binary, and the other half is a compilation step. The lightweight runtime library does some tracking and interception stuff that I'm going to cover in a moment. But first we need to take a look at the compilation step that does some signaling to the sanitizer, whether we are or aren't in a real-time context. So here's our real-time thread entry point. This is our dispatch callback. Now, most of you will be aware that as part of compilation, after we've parsed this code and got our AST, but before we get to our target-specific assembly instructions, in the middle there, what we have is kind of a more abstract intermediate implementation that is assembly-like. But this is nice because we can do optimizations in this domain without having to worry about the specific target. And it's here that if, sorry, one second, just that's called IR, intermediate representation. So it's here that if you've attributed your function with non-blocking, you tell Clang this is a real-time function, and you've activated the instrumentation, Realtime Sanitizer actually injects 2 function calls. One at the entry point to the function, which says we are entering a real-time context, and one at the last instruction before we return, saying we're exiting a real-time context. And what this is saying is everything in between needs to be non-blocking. Those functions are defined in our runtime library, and essentially what they do is they just keep track of how deep into this non-blocking stack we are. It's just incrementing and decrementing integers. But we also do some other cool stuff. This is our function interception. And what this allows us to do is to reroute any function call made by the process to a function like malloc to our own implementation. And that uses some kind of neat platform-specific tricks. And you know, this is exceptionally powerful for us because we can do whatever we want. We can do whatever we want in this implementation here. We can choose to behave normally. We can return the result of the real malloc, right? And that would be nice. Or we can do some other stuff. We can check if we're in a real-time context. We can ask, are we between real-time enter and real-time exit? Are we supposed to be non-blocking? Has something in our process tried to call malloc when it's supposed to be non-blocking? That's the key. If the answer to that question is true, we've got a big problem. So we print a stack trace and we kill the process. So we've seen how powerful interception is. It allows us to detect any function call, assert that we're not in a real-time context, and we can choose whether to error or behave normally. We'll behave normally in kind of non-real-time functions. Of course, it's not enough to just intercept malloc. So what functions do intercept? Well, Realtime Sanitizer is concerned with non-blocking functions. So our aim is to basically intercept anything that we think could block. So allocations aren't the only thing that could block. Deallocations need to go to the operating system and give back the memory. Locking a mutex, unlocking a mutex, waking up some threads waiting on a condition variable, and so on. And does anybody recognize something in common about these functions? maybe where they live, where they're defined. Yes, thank you very much. 10 real-time points to whoever that was. libc, yes, very good. So the reason we intercept in libc is hopefully becoming clear as we look at the physical layers through which a user's application interacts with the operating system's kernel. We're using memory allocation here as an illustrative example, just to essentially show that it would be infeasible for us to try to intercept every function in a user's application. I mean, we won't even know most of them in advance anyway. It's impossible. We could think about trying to intercept all allocation-like functions in the C++ runtime library, but there's only a handful of functions that directly allocate memory in the C runtime. So that's the thinnest point in the funnel. And crucially, it's also the last point before this, real blocking boundary here, right before we go to the operating system. So this is really the perfect place for us to do our interception and try to catch allocations and other blocking operations. Here's a non-exclusive list of the functions that we intercept. This is just here to illustrate that there's a lot of things we need to do, but not crazy loads. Okay, we need to think about memory allocation, threads and sleeping, file systems and streams, and we also want to make sure we're not trying to do any HTTP requests on our hot paths. We think something would really have gone wrong if we get there, but for completeness, they're there. Okay, so just a quick recap to hammer home this message. 2 steps: attribute our real-time functions with non-blocking, compile with our feature flag, and reap the benefits. All right.
Excellent. Thanks, David. Actually, funny story. I did work on a code base that called HTTP requests from the audio thread, and that was indeed quite bad, and we had a lot of dropouts that I needed to fix. So alongside Realtime Sanitizer, which again is the runtime approach, we have the new performance constraints attribute system, which is the compile time approach. It asks the question, what if you could just compile your code and know if it was real-time compliant? So let's dig into the examples. First off, there are 2 very important flags that you're going to compile with. The first one is function effects, and the other one is perf-constraints implies no except. This is maybe one of the longer flags, but I promise it will become clear while it's named that in a little bit. More crucially, there are 2 new function attributes that kind of key off of this. The first one is called Clang non-allocating, which, as it implies, says this function during its invocation will never allocate. And look at it, it's our good friend non-blocking. So this is a statement you put on your function saying that no blocking calls can happen during this function or any function that this function calls. This is one of the first times to note that, again, these tools were designed in conjunction to work together. So you can attribute your top layer callback as non-blocking and get the benefits of both performance constraints and the real-time sanitizer when you want to run it. Let's take a look at this. So Clang non-allocating. You have a function that you want to make sure you never allocate in. You are going to add the Clang non-allocating attribute to the function, and you'll compile with our friendly warning flags. And you get a very nice message here saying a non-allocating function must not allocate or deallocate memory. Incredible. Really straightforward what's going on here. In a similar way, non-blocking. If your dispatch loop should be non-blocking, which it is, I would argue, you add non-blocking to it, and you get another warning message. Non-blocking function must not call non-blocking function std mutex lock. I'm glad to be doing this presentation so I don't have to do the triple negative anymore after today. Non-blocking function should not call non-blocking function std mutex lock. All right, in this way, we build a hierarchy. We build a hierarchy where non-blocking is the strongest guarantee, and it implies non-allocating. In the same way, Clang non-allocating requires no except. So I think this is really logical, and let's dig into the example here. So Clang non-blocking implies non-allocating. We talked about earlier that a malloc is possibly non-deterministic in its runtime, so it makes sense that in a non-blocking context, you would also not allocate. If you try to do this with dispatch being marked as non-blocking, you get a warning message similar to the one we see before. Non-blocking function must not allocate or deallocate memory. Similarly, to throw an exception, you must allocate it first before it's thrown. So it makes sense that non-allocating requires no except. If you try to attribute foo as non-allocating, you get another similarly helpful warning. Non-allocating function should be declared no except. This is that Wperf-constraints implies no except we saw earlier. So in this way, remember this slide. If you're asleep in the back, I don't see anybody asleep right now, but if you were, this is really important. Non-blocking is non-allocating and also no except. Non-allocating is no except. It's this hierarchy with non-blocking being the king of them all. So attribute your top level real-time callbacks as non-blocking, and you get to use both performance constraints attributes as well as the real-time sanitizer. Perhaps more interesting in the performance constraints attributes is the function restrictions it puts in place. As you may well know, a normal unattributed function can call whatever you want. It makes sense for it to call non-allocating functions and non-blocking functions as well as any other function. Everything is okay in a non-attributed function. When you move to a non-allocating context, you can only call things that also have your similar restraint. You can only call other code that doesn't allocate, and because we know non-blocking implies non-allocating, that is also safe. Non-blocking is the most restrictive of them all, so non-blocking code can only call other non-blocking code. You can only call your constraint or stricter. If we have this case here where our process block is marked non-blocking and we try to use unknown function, which is unattributed, we get our friendly warning with the triple negative, non-blocking function must not call non-blocking function, unknown function. We can fix this, of course, by changing the declaration to be non-blocking, and this compiles as we'd expect with no warning. So non-blocking functions can only call other non-blocking functions, and function constraints may only call their constraint or stricter. All right, we're gonna do a very fast game of does it compile? Please raise your hand. I'm just gonna call in the first person I see. Does it compile? Can non-blocking process call non-blocking foo? Raise your hand if you have an answer. Yes is the answer. Throw it over there. All right. Can non-blocking process call unattributed foo? Somebody raise your hand. We have limited candy here. Yeah, thank you. No, it cannot. So non-blocking process cannot call unattributed foo. It's not a stricter constraint. Can non-blocking process call non-allocating foo? Raise your hand. Over there in the blue shirt. No. The answer is no. Thank you very much. Same issue. Non-blocking function can only call other non-blocking functions. And I think last but not least, can non-allocating process call non-blocking foo? Raise your hand. Yes. Right there in the tan shirt. Excellent. 100%. When David was doing this yesterday, he was getting everyone wrong on purpose to mess me up. So.
Good candidate.
All right, so alongside these function call restrictions, there's a really nice part of the performance constraints attributes that help you convert your large-scale code base much quicker. You can see how this could kind of be laborious to go through a big legacy code base and convert everything all at once. And this is called constraint inference. If your function is defined in the same translation unit as the non-blocking function it is used in, the compiler is smart and can figure out what the constraint should be. In this case, we have our process block being called non-blocking, and we have an unattributed defined here, which I think we could all agree in the previous slide we would have said that's a little sketchy. But compiler is smart enough to look at the function body, see that nothing is going on that breaks our non-blocking guarantee, and the compiler is happy. Once you change your body of your function to do something that isn't okay with non-blocking, we get another helpful warning saying it cannot be inferred non-blocking because it calls non-blocking functions did mutex lock. Unfortunately, there is a little bit of a limitation here. It only happens when the definition occurs in the same translation unit. So in this case, where we have some third-party function called defined here, it will try to do the inference, but fail. It said it cannot be inferred non-blocking because the definition is not in this translation unit. Again, really love these warning messages. It really points out exactly what's going on here. You can get around this if you want to. One helpful way to get around this is redeclaration, especially when you're using third-party libraries where you might not be able to control the code that you're using. It might be useful to add non-blocking to defined here, or defined elsewhere, rather. But you have to pinky promise me right now that you looked at the source code and it absolutely is non-blocking. You guarantee that it is non-blocking. There's actually a bit of a problem here. If in your third-party source code this does take a lock or does allocate, this can compile without warnings even though it's incorrect. So this is a little bit of a hole that you can fall into with performance constraints. This is actually a really good time to shout out Realtime Sanitizer, because by running it on this code, we could empirically test if this lock is taken on this path. So again, these tools are designed to work together. All right, top layer summary for everybody who wasn't paying attention. These are our warning flags that we care about. We're going to compile with these warning flags. When they are on, we get specific changes to functions that are marked non-blocking and non-allocating. For real-time context, the non-allocating keyword, or non-blocking keyword, is key. Specifically, it disallows any allocations. It disallows any functions that it can't figure out if they're non-blocking or they're not declared non-blocking. And it won't even allow you to initialize static local variables because the compiler can put in locks in some circumstances. So this is how you use the performance constraints attributes. All right, we just saw Realtime Sanitizer, the runtime approach, performance constraints attributes, the compile time approach. We're going to talk about comparing and contrasting and some practical tips for these tools. But first, we want a brief interlude. We want to cover our butts for everybody in the room. Neither Realtime Sanitizer nor performance constraints can fully guarantee 100% that your code is real-time safe. This is crucial to Grok. What I mean by this is Realtime Sanitizer has its blind spots. It can't guarantee your processor gives you the right time slice or isn't doing other things during your callback. It can't guarantee your code runs faster than the allotted time. It can't detect handwritten assembly calls if you're insane enough to do that directly. Not all the libc wrapper functions are implemented. And there's no detection of non-deterministic loops, at least not yet, things like infinite loops and cast loops that might be problematic. So some of these highlighted ones will never be detected in a sanitizer context. It's just outside the scope of what a tool like this can do. So we can't fully guarantee real-time safety if you're past these tools. So similarly with performance constraints, it has its own blind spots. A lot of them are similar to Realtime Sanitizer, and it has that additional blind spot we just saw of misdeclared functions. Sometimes you can get into a state where you've kind of lied to your compiler and it can't be your friend anymore. So going back to this slide, neither RTSAN nor performance constraints can fully 100% guarantee real-time safety in your code. But the point of these tools is it makes writing real-time code faster and safer than ever before. So they're an improvement, they're a step in the right direction. All right, all the legalese is over. You guys have read this fine print. You're ready to use these tools. Let's get into some of the practicalities.
All right. Thank you, Chris. We promised 50%. We are just over 50%, so let's get straight to it. So, yes, these tools were designed to work together, and there are some similarities between them. They both solve the same problem, or at least try to solve the same problem. They both use the same attribute, Clang non-blocking, and they have the same caveats. No real-time safety guarantee. But this is pretty much where the similarities end. All right, there's some significant differences, and we're going to dedicate the rest of this section to exploring those. So let's start with the biggest difference. You might have clocked this already, but Realtime Sanitizer is only operating at runtime. Performance constraints only operating at compile time. Might be obvious, but what does that mean for what you can infer about your code? What does that mean for you? So with Realtime Sanitizer, if your code runs without crashing, without erroring, it's compliant, right? Performance constraints, if your code compiles without warnings, it's compliant, right? Almost. There's some caveats, but this is in essence the message. Right? With Realtime Sanitizer, if your code runs, it's compliant as long as you have hit every path in your code. Right? That's key. Let's say you have something in your callback that does, say, allocating only in specifically rare circumstances. Right? If once a leap year you allocate a megabyte, then you're basically never going to catch that in your test suite. So, what's our recommendation here? Well, extensive unit testing with Realtime Sanitizer enabled. Try to hit every path in your code with your unit tests. And we'll see in the next section, Chris is going to show us that the cost of Realtime Sanitizer and runtime is actually pretty negligible. So we'd recommend doing your QA builds with Realtime Sanitizer enabled as well. All right, there's of course another caveat on the performance constraints side, and that is, yes, if your code compiles are warnings, it's compliant only if you actually pay attention to those warnings and fix them, right? And only if you redeclare things in third-party libraries correctly. So a recommendation here is promote those warnings to errors and audit third-party code with Realtime Sanitizer. It's almost as if this is just normal, good engineering advice. So you will have heard this advice before. So that's it. All right, over to Chris.
All right, false positives and false negatives. Where do these tools kind of fall over a little bit? Realtime Sanitizer is kind of the optimist. Let's say its mantra is innocent until proven guilty. Everything's fine until you allocate and then you're going to jail. This is the rare condition allocation that David just talked about. If you only allocate on leap year, your QA department didn't catch that. There's no way of Realtime Sanitizer to do that. Or maybe we didn't intercept that specific libc call yet. Performance constraints is kind of the pessimist. It is guilty until proven innocent. And maybe this is best shown by an example. So is this real-time safe? Somebody raise your hand. Is this real-time safe?
No.
The answer is it depends. That is exactly the problem. That is perfect. Thank you. You'll get your $5 afterwards. That is the perfect example of why it's context specific. What I didn't tell you and why this was a trick question is earlier in our main thread, we reserved enough space to do this operation as many times as we want without running into any problems. Well, what do our two new tools say about this? The performance constraints attributes say, this is not okay. This isn't okay in this context. Pushback allocates in some cases, and in other cases it doesn't. Further, we couldn't even do our redeclaration trick here. It would be inappropriate to redeclare pushback as non-blocking because in some paths it allocates memory, right? However, Realtime Sanitizer is happy with this code. In fact, it tests what actually did happen during this path. So it says you reserved the right amount of space, you pushed back in a real-time context, but you had enough space for me, so everything's all good. All right, so performance constraints attributes had a bit of a false positive here. It showed an error when this code didn't allocate. It says this method is not always non-blocking free. Pushback sometimes allocates and sometimes doesn't, so I don't really know what to do with that. Realtime Sanitizer didn't error in this case. It knew that we had enough space in it and we didn't allocate in our real-time context. And it says this method is compliant on all of the paths that we hit. This is, again, a great way to use Realtime Sanitizer in ways to probe your implementation of the STL, probe third-party libraries, and kind of see empirically what's going on in the hood. Again, it can't give you 100% certainty, but it can give you an idea of what's going on under the hood. So performance constraints analysis has no false negatives. It will never miss an allocation. It's always correct in that regard. But sometimes it's maybe a little overzealous. Maybe pushback, it doesn't have all the context to figure it out in that circumstance. Realtime Sanitizer has no false positives. It says everything that I saw in this call, in this run, was compliant and we're happy with it. But maybe you could stumble into some case like the leap year example. You only allocate on leap years. Maybe we didn't intercept the call correctly yet. So you might miss something using Realtime Sanitizer.
All right.
Oops, sorry.
But that's all good. So let's investigate the cost of each one of these tools. So yes, Realtime Sanitizer has a non-zero runtime cost. We're going to see that it's small, but it's non-zero. And performance constraints attributes, converting a larger code base, we think has an engineering cost associated with that. So we're going to compare those there. So let's first look at the runtime cost of Realtime Sanitizer. Now, this really happens in the intermediate representation domain, but I'm going to put it here just to illustrate. We've inserted our context entry and context exit tracing function calls on our non-blocking function. What's really happening under the hood here is all we're doing is incrementing and decrementing some thread local integer, just to keep track of how deep in that non-blocking stack we are. So for our real-time functions, those which are attributed non-blocking, yes, every non-blocking function has an additional increment and decrement. Also, because of the way that the sanitizer internals work in the IR domain, it may or may not interfere with some inlining optimizations. If you're particularly unlucky, it might get a bit of a slowdown, but maybe not. What about the non-constrained function case? What if we have some kind of lower priority UI thread that is happy enough making memory allocations? Well, this make unique, we're all happy that that's eventually going to result in something like a malloc under the hood. But if we've got our real-time sanitizer enabled, we're going to intercept that. It's going to call our own implementation. So let's peel back one more layer. What's happening under the hood there is we're checking whether we're in a real-time context. So we're just inspecting the state of some integer and then calling the real malloc. In reality, there's a couple of other little checks we need to do to make sure we're initialized properly, but it's minimal. We're effectively just making 3 function calls that just check some integers. So yes, when the sanitizer is enabled, there is a minimal runtime cost. And just to be 100% clear, there is of course 0 runtime cost when the sanitizer is not enabled. Let's look at the engineering cost for introducing the performance constraints attributes, especially in a larger existing code base. Now, you just downloaded LLVM 20, you're excited to try this out, so you put Clang non-blocking on your real-time thread entry point. You compile. What do we expect? We expect some error. Yeah, that's great. We were expecting that. Must not call non-blocking function foo. So what do? We go find foo. We double check it. We make sure it doesn't do anything bad, and we attribute that and compile again. And oh dear, we got the same error. That's because bar is not attributed non-blocking. So let's go find bar in our code base, check that it's okay, attribute it non-blocking, compile again. And this is getting to be quite a lot now. And you may ask yourself, like, what have I got myself into here? Is this my beautiful code base? I'm not sure. But don't worry. We'll see in the next section that there is a way to do this incrementally. We don't have to do it all at once. So yeah, all is good. So yes, there is some upfront effort to converting a legacy code base to performance constraints attributes to get it to a state where it's happily compiling. But it's totally worth it. Completely and utterly worth it, we think. Chris and I at least envisage a future where, real-time libraries have these performance constraints attributes as a really key part of their public APIs. Maybe even one day they might get standardized and put in the standard library. And of course, to be 100% clear, for new projects, this is not an issue. You can start using it from day one. No extra cost there. All right.
Excellent. So let's say you have a false positive or some section you don't want to address yet. How do we disable each of these tools? Realtime Sanitizer, we'll see in a second, you can disable it with a scoped disabler object, but let's start with performance constraints attributes. We can disable this with a call site macro like you can do with many warnings. So this code that just caused David Byrne so much consternation, we got our new code base and we want to slowly adapt it. Well, Doug, the author of the performance constraint system, cleverly gave us this macro in his initial proposal of things. And what it does is temporarily disables the warning and then enables them afterwards. So you can envision this as a Band-Aid that you put in your real-time callback. It's big and scary. You're not going to miss this in the future. It's always going to be a little on your shoulder. Hey, I should really fix that. But it unblocks you while you can address this bit by bit. So you put this on all of your calls in your top level real-time callback, and slowly and painfully you can peel back the Band-Aid, which is here. Oh, I hear you're supposed to do it. All right, disabling RTSAN. Perhaps you have a lock or something you take in a situation where you're overflowing or you have an error. Your real-time guarantee is already way out the window. What you do is you include this header file that ships with LLVM 20. You instantiate a scoped disabler object, which is a nice RAII saying, hey, just ignore this one for now. And this will compile and run without any warnings. If you're interested in other opportunities where it might be okay to sin in the real-time thread, highly recommend Fabian's talk, Real-Time Confessions in C++. It's not many times a C++ talk sends shivers down my spine, but that was one of them. It's a really interesting watch. All right.
Okay. And then let's look at the scope for using each one of these tools outside of LLVM. So with performance constraints, that is a feature of Clang in LLVM 20. Neither Chris nor I are the authors of that, so we're not aware of plans to get that into GCC or MSVC. We're pretty confident it'll get to Apple Clang eventually, but yeah, we're not sure about that. Realtime Sanitizer, it is possible to use with other compilers if you are willing to do a little bit of building and hacking yourself, and that's what the rest of this section is dedicated to. So if this goes by in a bit of a blur, don't worry, we have instructions for doing this on the Realtime Sanitizer helper GitHub repo. I will put a link to this at the end of the section as well, so don't worry about it if you can't write it down. What you're going to do is you're going to go to that repo and download the RTSan standalone header and activate the sanitization with this conditional macro here. If you initialize it early on in your process, and then everywhere you would have put Clang non-blocking on your real-time functions, if you instead introduce one of these RAII classes, scope sanitize real-time, this does the same thing. This effectively just calls real-time enter on construction, real-time exit on destruction. And so you can set up a real-time context that way. If you build and link the runtime from LLVM 20 into your project, then you can reap most of the benefits. That's great. As long as your compiler supports linking libraries and including headers, should be good to go. We've tested this on Apple Clang 15 and GCC 14 on Linux. And again, instructions are on the helper repo here if you're interested. So we're at the end. This is our summary. How do we use the performance constraints attributes? We attribute our real-time functions. We compile with our warning flags. And we reap the benefits. How do we use Realtime Sanitizer? We attribute our real-time functions. We compile with our feature flag. And we reap the benefits. Here's a summary of the bits that are the same and different between these two tools. This is what we spoke about today, but the main message is this one. Both tools were designed to complement each other, so use both. And let's write better real-time code. Big thanks to the people on this slide for their contributions. They've been invaluable. And I would like to invite any questions.
Yeah, if you have questions, please come to the microphone so everybody in the future can hear you.
Yeah, so I have two questions. Number one, does the enter real-time and exit, does that rely on thread local storage in order to ensure that different threads are? Okay.
Yes.
Yes.
Yep.
Yeah, yeah.
And the second question is, so I do mostly embedded systems, bare metal system stuff. Do you guys have an idea of what the overall cost would be if I was to bring that onto an ARM chip?
In terms of runtime?
Flash size and maybe a little bit of RAM size if you have that information.
Honest answer is no.
Okay.
Yeah,
But,
great question.
Yeah, good question. We can find out.
Yeah,
Okay.
be in touch afterwards. We can either give you the tools to determine that, or we can help you determine it yourself.
Fantastic.
Yeah, thanks.
Hi, thanks. I'm wondering, how does the attribute work with virtual functions? Does the whole class of functions have to have that attribute?
Excellent question.
It has to be on the most. It has to be on the concrete function.
The concrete.
Yeah.
Okay.
Yeah. So
And
it doesn't
if
get
you
inherited.
If you had one concrete that satisfies it and one that doesn't, would you
Good question.
get the correct result?
I don't know.
Okay.
Thanks
Yeah,
for the question.
we're also still getting used to, especially the performance constraints attributes, which introduce the attribute itself. So again, we can help you find that answer for
Okay,
sure.
Great, thanks. Yeah, this
Yeah.
looks great.
Thanks.
Thank you.
So first of all, this is amazing. Thank you so much for doing this. I wish we had this 10 years ago. It would have saved many people lots of pain. There's one thing that worries me there, which is the requirement of having no accept.
Sure.
Because you have this thing called the Legos rule that you don't put no accept on a function that has a precondition. And we might get a feature that lets you express that and say, hey, it's a bug to call this function with a negative index or whatever. And then, even if you know that it never throws an exception if you call it correctly, you don't want to put no accept there, because if you do call it incorrectly, you don't care anymore about any real-time stuff anyway. You have a bug already, you know that. Yeah. So at that point, throwing an exception is a valid way of letting the user know, hey, something is pretty bad here.
Yeah.
But it seems like your approach would just make that impossible, which is the one thing that worries me a bit, that you have to put no accept on there, because a lot of it's usually not something you want to do unless the no accept actually makes a difference. Something like vector pushback, right? It actually queries whether something's no accept and chooses a different algorithm. If it is, that's a good use case for no accept. But especially for functions that might have preconditions, you don't want to put no accept on there. And it seems like there's a bit of an unfortunate interference there between the two features.
Yeah,
worries me a bit.
So two things. One, this is totally in progress, so we can give that feedback to Doug, who is the author of the performance constraints attributes. The other one is it's just a warning at this point. You as the code implementer can ignore that warning, and everything's okay. It's not a requirement. It's not a strict requirement. It doesn't change the underlying implementation of the code, but it warns you in that case if you listen to that warning flag.
It's a little bit like the other thing you showed that you do have, where you can opt out. You can say, well, now in this situation that something went wrong anyway, so I'm going to opt out of this so I can do whatever anyway. Totally. And it feels like throwing exceptions should also be one of those things.
Yeah, sure. Yeah, I think that's valid. Let's talk afterwards. I think that's perfectly valid feedback.
Thank you for the fantastic work. I love this tool.
Yeah.
It's amazing. Thank you.
Thanks.
Yeah, thanks again for the talk. I have a two-part question. One is, did you do any work with libc++ to add these annotations, or are you just relying on the implicit ability for the performance constraints to go through any of the headers in the standard library?
So the interceptor on the libc level is
just for the performance constraints. So
for the performance
non-blocking and non-allocating. Is it just relying on the implicit ability to do that on all the headers of the standard library?
So yeah, there's. Oh, go ahead.
It's entirely in the Clang front end, I think. I'm not dealing with this. I'm not hugely.
Yeah, and there's some work being done to mark built-ins as safe versus not safe or something like that. So there's some work verifying that this is correct and okay in performance constraints versus not. So.
And is there any opposite version of the non-blocking? Because you said you can't determine oh, this is an unbounded time, this function. So can you say, oh yeah, I know machine twister is not real-time safe, so I'll put it's blocking, or just don't call it. Is that available?
I wonder if we have the slide for it up. The quick answer is yes, very soon. So there exists an attribute right now that is called blocking, and it triggers the performance constraints attributes. We just didn't have time to talk about it. But the idea is the same in Realtime Sanitizer, that eventually those will warn or crash your program as well. So yes, awesome. you with the programmer, you know what is real-time safe and not. You can explicitly say this is blocking in this case, and you cannot call it from a non-blocking context.
Cool. Well, excited for it to eventually be an Apple Clang.
Yes. Us too.
I might be mistaken, but I believe that local statics can be initialized at compile time and not just at runtime, in which case you wouldn't have any kind of mutex acquisition on initialization. Okay. So it seems a little overzealous to look and see any local static as being a reason why something should be non-blocking.
I mean, nice point. I would refer you to the author of the performance constraint stuff, and I'm sure he'd love to hear that feedback. Yeah,
definitely. So in the Discord chat afterwards, we can post where some of these were proposed and where they were discussed and stuff like that. And I'm sure he'd love to hear that feedback. Again, we know significantly more about real-time sanitizers than we do performance constraint, but they kind of came together all at the same time. So I think that feedback is valid, and we can pass it on to the right people.
Hey guys, thanks for the great talk. I had a question about Realtime Sanitizer. Would it potentially be possible to add some of my own functions to the sanitizer so that just as kind of a house rule, if I call this, know that it isn't real-time safe?
Yeah, definitely.
Just the opposite, to take some off.
Yeah, that too.
Yeah.
If I implement malloc.
Sure, yeah. So the first one, there's a pull request up in the LLVM project at the minute to introduce the ability to mark one of your functions as blocking.
Cool.
That will then error if you call that in real-time context. And then the opposite, we do have a prototype where you can kind of add suppression lists in Realtime Sanitizer options that you pass through at the command line. So it's coming. It's not there yet, but it is coming.
Awesome, thanks.
Thank you for the talk. Great tool. Looking forward to use it. Quick question is, does it conflict with other sanitizers? Sometimes I want to build maybe one or two, three sanitizers together, but some of them they conflict. Is this one conflicting with like memory or address?
Yeah, definitely. It doesn't work with any other sanitizers active. Okay. It tries to intercept the same things that address sanitizer tries to intercept, so they can't work together, unfortunately. Thank you. Great question.
Any other questions? All right, with that, a couple more things. We want to get together with other real-time programmers, other audio people, video people, any other things. If you're free on Wednesday at 6 p.m., this is totally informal. This is just us announcing that we'll be there. Come hang out, have a beer. We'd love to chat with you more. And also, if you'd like to help improve Realtime Sanitizer, come work with us, especially if you're a Windows dev or an Android dev. You notice we didn't call any non-Unix system calls. There's a glaring hole in this project right now. Other architectures, things like adding interceptors are really, really easy. Testing out, we're trying to see if we can determine unbound loops at compile time or runtime, and just general feedback and testing. I know when this is my first big open source contribution, and I know somebody at the end of a talk I wish said, this is how you can help. I'm telling you, in like 10 lines of code, you could add an interceptor, and we would be thrilled to have you. So if you're interested in contributing, reach out to us. We'd be happy to help. But thanks for coming. Come to the Real-Time Programmer Meetup at 6 p.m. on Wednesday at the sports bar right over here. Thanks again for attending.